Hi, welcome to Module 4, Part 2 on Bayes' theorem. Now we'll be looking at what Bayes' theorem is about. It's named behind Thomas Bayes, who provided a method for revising probabilities to reflect new probabilities, basically to understand posterior prior probabilities. The marginal probability of an event B could be revised after another event A is considered to give a posterior conditional probability on the probability of B. Bayes' formula basically would look as P of B given A is P of A given B times P of B over P of A. It begins with this formula, and however, in some situations we might not have P of A, and therefore its more useful and common form of Bayes' formula is P of B given A is P of A given B times P of B over P of A given B times P of B plus P of A given B dash and P of B dash. That's the complement of B. Let's have a look at how Bayes' theorem works with a small example. Now consider a pregnancy testing kit and a clear record of its determining pregnancies based on the test that it gives. You know, the over-counter test kits that they give. Now in this case, the test tests positive and the woman is pregnant is about 96% of the time. And the woman is pregnant while the test yields a negative result is about 4% of the time. The test is positive, but the woman is actually not pregnant is about 1% of the time, and 99% the test is negative when the woman is not pregnant. So this is the test track record. If the woman is pregnant, it's about 96% plus 4%, 100%. That's a false negative 4% of the time. And if a woman is not pregnant, what's the track record? That's a false positive. Let's look at it with a simple example with numbers. Let's say there are about 60% of the women who actually purchase the kit are actually pregnant. Now, if about 1,000 women use the test kits, the results would look something like this. That's about 96% of the 600, because 1,000 women tested and 60% are actually pregnant. That's 600, and 96% of 600 is 576. Similarly, it's about 4% of 600 which indicate a negative test, although the woman is actually pregnant. Now, how does Bayes' theorem work in case of this particular situation? Of the 580 people who have been tested positive, 576 are actually pregnant. So the desired probability is probability of being pregnant given the test is positive is 576 of 580 is about 99.31%. So if the test proves to be positive, then there is 99% chance that the lady is pregnant. Now we will use the formula to derive the same 99.3%. Let's first define the events to be A as positive test and A dash the complement negative test, B being pregnant and B dash not pregnant. From the tables we would get the values for probability of positive given pregnant as 96%, probability of positive given not pregnant is about 1%, and probability of being pregnant itself, B, is 50%. Similarly, the complement of each event is probability of negative with pregnancy is about 4%, and probability of a negative being negative is 99%, and probability of not being pregnant is about 40%. So when you apply Bayes' formula here, it would be 0.96 times 0.6 by 0.96 times 0.6 plus 0.01 into 0.4. So that would give you 99.31%. So there's 99% chance that the woman is actually pregnant given the test is also positive. Prior to the test, we were looking at the probability of being pregnant at 60%. However, the posterior probability of having tested positive will inform that 99% chance that the woman is actually pregnant. So Bayes' theorem shows us how to revise our prior probability of 60% chance of pregnancy to get the posterior probability after a test to be at a higher level. So Bayes' theorem is very useful in calculating conditional probability. So if you have to visualize using a tree diagram, that's about 60% chance the lady is pregnant. Sorry, that's about 40% not pregnant. It's about 96% chance that you're tested positive and 4% you're negative, 1% you're positive and 99% negative. So the two branches which show the positive are pregnant positive and not pregnant positive. So the value is calculated by multiplying. So you add the probabilities to get the denominator of the fraction, whose numerator is b intersection a. So the general form of Bayes' theorem allows the event to be polytomous, more than one occurrences, rather than having only b and b dash. This is the general form of the formula. So p of bi given a is p of a given bi into p of bi over p of a given b1 into p of b1 plus a given b2 into b2, and so on. There's another example here with a hospital about the trauma centers. Based on historical data, there were 3% cases at the trauma center which could result in a malpractice suit. So let B1, B2, B3 be the three different hospitals with the trauma centers, and let's define an event A as a malpractice suit being filed. So the conditional probabilities of a malpractice being filed, given it's from hospital 1, is about 0.001, and similarly for B2 and B3. And when we apply the general formula for Bayes' theorem, P of B1 given A is P of A given B1 times P of B1 over A given B1 times B1, B2, B3. So the probability of B1 given A is 0.1389. We could calculate the same for B2 given A, B3 given A. So we can conclude in this case that the probability that the malpractice suit was filed and it was in hospital 1 is about 13.89%. So all posterior probabilities for each hospital can be calculated and compared. So that gives you the list of revised posterior probabilities. So let's say about 10,000 patients actually went to the hospital, and so based on the posterior probabilities and the marginal probabilities, you would have the contingency table filled up this way. About 50%, 30%, 20%. That's about 3% and the remaining percentage. Let's now use the frequencies to find the probabilities for Bayes' theorem. So B1 given A, that's a malpractice, it's in the hospital 1, given there was a malpractice suit being filed, is about 0.1389, taken from the previous calculations for marginal conditional probabilities. Similarly, for a suit not being filed is given in here. So visually, it would look like this. We have the three different collectively exhaustive events, hospitals B1, B2, and B3. And A is the event of filing a lawsuit, which is smaller. The different hospitals, a 50% chance in hospital 1, 30% in 2, 20% in 3. Now the whole sample space is actually reduced to the sample space with a lawsuit, A. So the revised probabilities are the relative areas within the event A. P of B1 given A, P of B2 given A, P of B3 given A. Thank you.